All right, so questions from the homework. What do you got? Yep. Number 4. Sure. So number 4 is we want to simplify tangent squared minus sine squared. Yeah, well, you could factor that. Do you guys see that you could factor it? Because it's a difference of 2 squares. It's one thing squared minus another. You could say, oh, you know what? I'm so smart. That's tangent x plus sine x times tangent x minus sine x. Like you could factor that as a difference of 2 squares, but like, what good is this? Factoring is usually good when after factoring, there are some common factors which cancel. You know what I mean? That's usually the benefit of factoring. Like you've got a fraction and you factor the top, and then you see a common factor and you get to cancel it. But that's not happening here. And there's not really anything worthwhile coming from that direction. So I don't think factoring is the right way to go. Ian? Yeah, let's convert stuff to sines and cosines and see what happens. That's kind of what you do when you don't have any better ideas, which is a lot of the time. So tangent squared is sine squared over cosine squared minus sine squared. Well, I've got one fraction minus, well, you might argue that that's not a fraction. I'd say it can always be viewed as a fraction, right? You can view this sine squared as being sine squared over 1. And then one thing you might try is combine those 2 fractions, right? Get common denominators and put them together. I don't really have any surefire way of knowing that that's actually going to do anything. It's kind of just a hope, really, at this point. But yeah, so let's get common denominators. You don't need to change this fraction at all to get common denominators. You just need to multiply this one top and bottom by cosine squared, and that'll do the trick. Do you guys see that? So no change to the first fraction, sine squared over cosine squared. This one I'm going to multiply top and bottom by that denominator, cosine squared. So I get sine squared x cosine squared x over cosine squared x. And, you know, now I'm ready to combine some fractions. So let's do that. Big fraction bar. The denominator stays the same, cosine squared. And I'm going to, you know, take this guy minus this guy in the numerator. Okay. So what? That doesn't look very good. In fact, that looks a lot worse than what we started with. Celia? You can factor out the sine squared. That's right. Look at the numerator. You see the 2 terms? Here's a term, here's a term. Those 2 terms each have a sine squared inside of them, right? They have a common factor of sine squared. And you can factor that bad boy out. Of the 2 terms. So that's going to leave me with what? Well, so here's my big fraction bar. I'll pull sine squared out, make a blank set of parentheses. Now what's left over? Pull sine squared out of itself, and you're left with 1, right? Pull sine squared out of this term, and you're left with cosine squared. Oh. Well. Okay. Fine. I mean, there aren't any common factors canceling, but there is a nice thing. Right? Ian?
1 minus cosine squared.
Yeah, 1 minus cosine squared. is actually just sine squared, right? So let's make that replacement. So sine squared x times this whole thing is just sine squared over cosine squared. I guess you could rewrite that numerator as sine to the fourth, but think about that. What would you do after that? Like, I don't know. I don't think that's really any better. Actually, sine to the fourth over cosine squared would not be the worst thing in the world, actually. But I think that my guess is the way they want you to see this is you can view this fraction in the following way. You can view it as sine squared x over cosine squared x times sine squared x. Do you see the advantage of doing it that way? Because what's this term here? That's tan squared. And I think that tan squared sine squared is one of the options. So that's what you're looking for. By the way, if going from here to here makes you feel a little uneasy, like you're not so sure why that's true, do you agree that if I put this thing over 1 and multiplied, I'd get back to where I started? Okay, so I hope that convinces you that these two things really are true. In general, it's true that AB over C, that is AC, A over C times B. That's the same thing. Or you could choose to put the C over the B. That's also good. That's totally fine. Yeah, that's what I'm saying. The one thing that you shouldn't do is make the mistake of thinking that this is A over C times B over C. Like division by C doesn't distribute over multiplication. Do you know what I mean? This is essentially dividing by C twice. So this guy is no good, but the other two are fine. Is that okay? What else? Yep, yeah. 10? Sure. Oh, it's the last one, isn't it? Probably hard. So 10 is tanks over 1 plus tangent squared x. Isn't 1 plus tangent squared something nice? I think it's secant squared. But I'm not really sure. And like, I don't have a list of the identities in front of me. I really swear I don't have the other Pythagorean identities memorized. The only one that I know is this one. That's all I know. Because you should be able to just rederive them. Like you're not going to forget this one. You know what I mean? Like that one will be etched into your brain. You're not going to forget that. As far as the other two, you can just derive them really easily. You guys did derive them. Yeah, Miles? You can divide it by cosine squared. Yeah, if you remember, to get the other Pythagorean identities, you just take the original Pythagorean identity, which is this one here, and divide everything by either sine squared or cosine squared. Divide everything by sine squared, you'll get one of the other Pythagorean identities. Divide everything by cosine squared, you'll get the third one. I'm looking for the Pythagorean identity that involves tangent squared. So if I want to get a tangent squared, I guess I should divide everything by cosine squared, because if I do that, I'll have sine squared over cosine squared right here. The resulting identity will involve tangent. Is that okay? Let me just do it in my head. Divide everything here by cosine squared. Okay, divide this by cosine squared. You've got sine squared over cosine squared, which is tangent squared. Cool. Plus, divide this by cosine squared. That's just 1, right? It's cosine squared divided by itself. That's 1. Equals, okay, this guy divided by cosine squared. That's 1 over cosine squared. What's 1 over cosine? It's secant, right? So 1 over cosine squared is secant squared. Okay, like I promise, like I never remember this for more than like 30 seconds. I just rederive it. Like, it's very easy to rederive. Anyway, so this guy in the denominator is secant squared. So I think probably I should just make that change, right? So 1 plus tangent squared, that's really just secant squared. My instinct is that if I convert everything now to sines and cosines and like do some keep it, change it, flip it stuff, then like some things will cancel and we'll be happy. Well, I don't know if we'll be happy, but we'll solve the problem. Okay. So yeah, I'm gonna just convert everything to sines and cosines. So tangent, that's sine x over cosine x, and secant squared, that's 1 over cosine squared. So I've got one fraction divided by another. So that's going to be keep it, change it, flip it. That's sine x over cosine x times the reciprocal of the bottom fraction, cosine squared x over 1. And now what do you notice? Oh, right. Levy? Yeah, the cosines cancel. I saw you making a gesture. I mean, there's 2 copies of cosine here, right? So after canceling this common factor of cosine, you're still going to be left with 1 factor of cosine, right? So it just won't be squared anymore. So I think the only, there's nothing left in the denominator. It's just a bunch of 1s, right? Like that's like 1. So I think the denominator is essentially gone. Like there is no more denominator. All that's left is the stuff in the numerator, which is sine times cosine, which I don't think it's going to get any better than that. That should be one of the answers. Is that okay? Okay. Can probably do one more. Celia? 4D. Oh, 4B. Oh yeah, I see how to do that. Okay. So 4B is 1 minus tangent squared x over tangent x minus tangent squared x. I'm kind of tempted to like maybe rewrite. Yeah. Oh, wait, what? Oh, that's 3B. My bad. That was 3B. Well, you know what? I'll tell you what to do. You should factor the top and the bottom, and then you'll get a common factor that cancels. In case you didn't figure this one out. The numerator can be factored because it's a difference of 2 squares. I shouldn't write an equal sign. That's 1 plus tangent x times 1 minus tangent x, right? It's like a squared minus b squared. Factors as a plus b times a minus b. And then the denominator has a common factor of tangent, which you can then remove. So pulling tangent out of itself leaves you with 1. Pulling tangent out of tangent squared leaves you with just tangent. And then you've got a common factor, which is like this, ba-bam, ba-bam. And then, I don't know, so maybe that's like 1 plus tangent x over tangent x. And then my guess would be split the fraction, because if you do, you'll get like 1 over tangent plus 1, which is just cotangent plus 1. You see what I mean? I don't know how far into the future you guys can see with these. But yeah, that's, if you split the fraction, it's 1 over tangent plus tangent over tangent, which, like I said, is, and 1 over tangent is cotangent, right? They're reciprocals. So that's just cotangent x plus 1, and that's probably what they're looking for that one. It's a good problem. That's why I did it anyway, even though it's not the one that you asked me to do. That's 3B. Let's actually do 4B now, and that'll be the last one that I do. So 4B. for real this time, is quantity tangent x plus 1 squared minus secant squared x over tangent x. So we're just supposed to simplify that. I think the only good idea is to multiply stuff out. I think that's what you should do. Let me do that. If you multiply this out, let me give you a comment on this. Like when you have like one thing plus another thing squared, you know that's not just a squared plus b squared, right? Yeah, like that's a plus b times a plus b. If you should kind of know that if you actually multiply this out manually and collect like terms, you get a squared plus 2ab plus b squared. It's kind of worth knowing that. You don't have to know it because you can always just do it manually. But if you know that, it's, you know, you're going to save yourself some time. Anyway, that's what I got here. So if you actually take the time to multiply this out carefully, you're going to get tan squared x plus 2 copies of this times this, which is just 2 copies of tangent, plus this thing squared, namely plus 1 squared, which is just 1. Those 3 terms there are what you'll get if you carefully multiply this first thing out. And then we've got a minus secant squared all over tangent. I think 1 minus secant squared might be a thing. Yeah, like let me, because I wrote down the Pythagorean identity a second ago, right? Here it is. Tan squared plus 1 is secant squared. So if you rearrange this equation, you can rearrange this equation to obtain a 1 minus secant squared. Do you see how you can get a 1 minus secant squared from this equation? Subtract secant squared from both sides, and then subtract tangent squared from both sides. Do you see that on the left-hand side, you'll have 1 minus secant squared, and on the right-hand side, you'll have negative tangent squared. Okay, so that tells me that yes, indeed, 1 minus secant squared is in fact negative tangent squared. Yep.
Could you not just combine the tan squared x and the plus 1?
So the question is, can't you just say, hey, I've got a tangent squared here, and I've got a 1 over here. Couldn't I just put those 2 things together to get tangent squared plus 1, which is secant squared, and just kind of use this identity in the most direct way? Yeah, you could. My gut tells me that's the wrong direction.
No, because I think your secants will cancel right away.
Yeah,
If you turn
you'll have
tan x
secant
squared
plus
plus 1, then it's secant squared. Then secant
Oh, I
squared
guess you're
plus
right.
0.
Yeah, no, I guess the secant squares will cancel. The reason I was hesitant to do that is that I noticed that everything here is in terms of tangent except for this one function. And so I'm like, no, I want to convert this thing to something involving tangent, and then everything will just involve tangent, and surely that's going to work out nicely. Do you see what I'm saying? But you could also do it the way that you suggested, and apparently that will also work out. Anyway, I worked pretty hard to get this, so I might as well use it. So 1 minus secant squared is negative tangent squared. So that's tan squared x plus 2 tangent x. And then this whole guy we established is negative tangent squared. So minus tangent squared all over tangent. And yeah, I mean, hopefully you can see that something nice is happening in the numerator, right? This guy minus this guy, those guys cancel. So it's just 2 tangent x over tangent x, better known as 2. Is that okay? Okay. I'm going to show you one quick trick. take notes on this. I don't have a lot to add. You guys are pretty much mostly ready to handle any kind of trig identity. There is like one more thing that I should mention, the sort of technique that comes up once in a while. So the example that I'm going to do here. I'm going to try to prove the following identity. Cosine x over 1 plus. Yeah, I know what's going on. I promise it'll be okay. I mean, it's also, it's fine. It's also this guy right here, right? That's what I'm writing down. Okay. So that's what I'm working on here. I don't know if anything we've taught you would really get you this guy. Like I maybe I'm wrong about that, but the technique I'm going to show you, which is multiplying by the conjugate, I don't really know if there's another way of getting this one. Maybe. So like usual, I'm just going to work with one side of the equation. I guess you could take this side, convert it to sines and cosines, get a common denominator, smash it all together. To be honest with you, I don't know if that'll work or not, but I'm going to show you something that's pretty clever. I'm going to take the left-hand side. I'm just going to copy it. And looking at this left-hand side, do you agree that there's like really nothing you can do with this? You can't split the fraction. That's not allowed. Like you can only split the fraction if you have multiple terms in the numerator. Do you know what I mean? Multiple terms in the denominator, you can't split that. So there's no fractions, there's nothing to factor, there's nothing to multiply out. It's already in terms of sines and cosines. There's nothing you can do with that. The thing I'm going to introduce is sometimes called multiplying by the conjugate. You've seen the phrase conjugate a few times. Like, remember that the conjugate of A, if you've done complex numbers, then you know the conjugate of A plus BI is A minus BI. Or if you remember like simplifying complex root expressions, you know that A plus root B, the conjugate of that is A minus root B. Basically, the conjugate of an expression like A plus B is A minus B. So what I'm looking at is this thing right here, this 1 plus sine x. I'm going to multiply top and bottom of the fraction by the conjugate of that expression. The conjugate of 1 plus sine x is 1 minus sine x. So I'm just going to multiply both top and bottom by 1 minus sine x. Now, like, why would you do that ever? Like, you're clearly making it more complicated by doing. I mean, it's allowed. You can multiply top and bottom of a fraction by whatever you want, as long as it's the same thing on top and bottom. But how would this ever make things nicer? The reason it makes things nicer is that when you have an expression times its conjugate, what you have is the product of a sum and a difference. 1 plus sine of x times 1 minus sine of x. Do you guys see that? If you multiply out that denominator, something nice will happen. You're just going to get a difference of 2 squares. All right. I'll skip the arithmetic. You can do it manually if you want, but I'm going to leave the numerator alone. I'm not going to actually multiply anything out in the numerator. But in this denominator, I claim that if you multiply everything out, like 1 times 1 is 1, 1 times negative sign is negative sign, sine times 1 is positive sign, you'll get some cancellation, and all you'll wind up with is 1 minus sine squared x. It's this thing squared minus that thing squared, because you have the product of a sum and a difference. Or to see it another way, do you see that if you factor this expression, you get back to here? Because it's a difference of 2 squares. Anyway, now you hopefully kind of see the niceness about doing that, because 1 minus sine squared is really just cosine squared, right? Okay. Fine. So this is really just cosine x times 1 minus sine x all over cosine squared. And now you can see that some nice stuff happens, right? There is some cancellation. The cosine on top will cancel with one of the cosines on bottom. So that's going to leave me with 1 minus sine x over cosine x. And now you can split this fraction. This fraction can be split because the multiple terms are in the numerator. Whereas originally, the multiple terms were in the denominator. You can't split something like this, but you can split this guy. And if you do, you'll get exactly secant x minus tangent x. That's 1 over cosine minus sine over cosine, which is indeed secant minus tangent. Yep.
If you had like distributed on a
Yeah.
not the same answer.
I think, yeah. I think if you had distributed in the numerator, it would have been fine. You would have split the fraction and then there would have been cancellation, as opposed to cancellation followed by splitting the fraction. Anyway, look, this is called multiplying by the conjugate. First of all, it is something that you will not use often. And it is really something that you should only consider if you're really out of ideas. Okay. It tends to be useful when you have like a non-quadratic, like nothing squared in the denominator, like 1 plus sine. It tends to be useful for that. Anyway, the worksheet today are scans from a textbook that I used when I was learning this stuff. And the textbook scans are very nice for a couple of reasons. I'll just show them to you here. I'm assigning 17 through 42, which is 25 problems. A lot of them are not hard. They start easy and get more complicated. So you're going to do 17 through 42. I mean, it's kind of boxed on the worksheet, so you don't necessarily have to write that down. But what I want you to do is do 30 first. Do number 30 first. Because number 30 is just like the one I just did. Sine over 1 plus cosine. Do you see it's kind of similar? So I want you to do number 30 first. Start with the right-hand side because it's the more complicated side. Start with the right-hand side and do this trick that I just mentioned about multiplying top and bottom by the conjugate. So you're going to multiply top and bottom by 1 minus cosine. All right, and see if you can turn it into 30. After you see if you can turn it into the left-hand side. After you do that one, just go back to 17 and work through. Okay. Good.
Is it 29? So today?
Yeah, 29 is also similar. Actually, I think 29 is literally the one I just did. I think it's exactly the same one. Yeah. One thing I'll say, guys, you flip this over, a lot of them are done out. Like fully, like it shows you how to do them. And if you pay attention, you'll notice that they kind of come in pairs and like they'll explain the first one fully, like on the back, and then the second one they won't. Because it's so similar to the one that you just did. Does that make sense? So the back has explanations, so consult them if you get stuck, okay? And if you want to have some fun and go crazy, like, keep going. I mean, they get really quite wild. Like these ones down here, 65. I think that's a doozy. Okay.